Well, okay. Let's get started this time. It's a bad weather day, so we'll see when people can show up, maybe. Last time, we discussed the mathematical details behind the famous backpropagation algorithm. Right? We derived all of the formulas necessary to compute the gradient of a neural network through backpropagating a quantity which we call the delta of L, which is the sensitivity of the error function to the input at the layer L. Right? So for now, today, we put everything together and into a more formal form, and we write the pseudocode of this algorithm. So we are given the input, which is one data point, one example, right? And remember, we omit the subscript n because it doesn't matter which n it is the procedure is the same. Yeah, but just notice that we do this once for every single example. So we're given the sample, and then we're given the current parameters of the neural network. Then the output, of course, what we're looking for is this, the gradient. So it's a collection of all partial derivatives with respect to all of the parameters, which we call the weights of the neural network. Yeah, like that. And to make the backpropagation work, we have to calculate first some of those variables, the values of the input to neurons and output to neurons, right? There's S and X's. Right? So therefore, to do that, we have to run a forward propagation first. In order to compute all of these values, S of L and X of L, for all layers. Yeah? So after the first step, we have all of them. And furthermore, we can also calculate the current error, right, for this current set of parameters. And it is given by a comparison between the output of the neural network and the label Y for this particular example, right? And how to define the error depends on you. Do you want to do square of the error? Do you want to use the log loss function? Whatever, right? So here we just use the function g to represent that in general. Here, notice that we use a general form, unlike the example that we saw last time, which is we assume the output has only a single dimension, right? Here we have a general dimension for the last layer. Yeah, this could be potentially greater than 1, right? But you can still define your loss function based on that. We have seen how to do that for softmax or logistic regression. Then in the second step, we calculate the delta for the last layer. Right. I'm just repeating what we have seen already, just summarizing them in this pseudocode form, right? And for the last layer, just looking back at your notes, for the last layer, we'll take the derivative, or we'll take the gradient, because it's more than one, of this loss function at the last layer, like that, right? And then this will be element by element, or pointwise multiplication by this theta of prime, right? Yeah. We find this input sensitivity with respect to the last layer's input. And then once after the last layer, then we can backtrack for L going back from L minus 1 back to 1. You just do the following. You just calculate this input sensitivity for every layer, right? For every layer, you just use the formula we derived last time. It's been a few days, so you might not remember this exactly, but this is what it is. Looks like this. Yeah, you use the delta from the previous layer, multiplying the big matrix of weights. Now you have a vector, and then you do pointwise multiplication again by the theta prime at this current layer. Yeah. Yeah. And once you have this, and by our derivation before, this one simply tells you that the gradient with respect to the matrix, the weight matrix at this layer, L, is simply given by x of L minus 1 times delta of L transpose. Right? So it's a column vector x multiplying a row vector here, so you get a big matrix, which is exactly what you want for the partial derivatives with respect to that big matrix. Yeah? So now you have the gradient with respect to this layer's weights. Yeah? Then as soon as you finish this loop, going back to the first layer, then you're all done. Right? You have all of the partial derivatives that you need to put together to form the gradient. Yeah? And then you can run your gradient descent algorithm. At least one step of the gradient descent algorithm. Right? Okay? Nothing new here, right? We're just really just writing the formulas that we derived last time. Okay? Now, what is the complexity of this whole procedure? Well, the first line is a forward propagation. We know the forward propagation causes big O of Q complexity, right? Where Q is the number of weights. Yeah, this forward propagation. I hope this rings a bell. Yeah, and then the second step, it's just one layer. I mean, this cost really negligible. Yeah, there's really no cost there. How about this one? Step 3. All that we're doing is this kind of multiplication, right? Just multiplication like this. This is a big matrix. How many elements are there in this big matrix? Well, just the number of weights you have in the layer, right? Okay. So altogether, all this multiplication is just the total number of weights you have. Yeah, it's just a proportion of the number of weights you have. Therefore, altogether, this thing has complexity big O of Q. Yeah? And this is very different from the finite difference method that we discussed before, right? For the finite difference method, we say that every time that you update a single weight, you have to run the forward propagation once. And then there are Q weights, so you have Q times big O of Q. Here, we just run the forward propagation just once. Yeah? One forward propagation once, and then you calculate all of the partial derivatives already. Yeah? So let me write it down before I go to your question. So only one forward prop propagation to compute all of these gradients, all of the partial E, partial W, I, J, L. Yeah? Okay. You still have a question? No? Okay. So, this method is highly efficient compared with big O of Q squared when Q is humongous, yeah, millions, billions to trillion. Okay, so that's what we have already derived. Let's take a look at a small example quickly. The standard part of the example is not very exciting because it's just repeating. We can just use the formulas that we have to on the example. But at the end, we have some notes. I think that could be potentially a bit interesting and or new. Yeah. So we have two inputs, let's say 2 dimensions, x1, x2, and by our convention, we label them as layer 0, right? So like that. And then this is sent into 2 neurons. And then these neurons go to one last neuron, the output. Right? Yeah. So the output, of course, is x of L, but let's call it x1 of L, even though we only have one neuron. We just follow the convention of indexing. Yeah. And this, you know what? sorry about this. Let me make it just a bit of input here, because this is called S1 of 1, right? Just so that I have some space to put in this symbol here. Yeah. And the weight, of course, will be W11 of 2 over here. This one is W12. 11. This is 2, 1 of 2, right? The second neuron to the first neuron of the second layer. Yep. That's the weight. And then for the previous neurons, let's say we have this is x1 of 1, right? That's the, and this is x2 of 1, yeah, by our notation. And here will be S1 of 1. This is S2 of 1, right? This is the first layer, yeah? This is, we only have one hidden layer, yeah? Just layer, hidden layer 1 or just hidden layer. And of course, this is the output layer. Yeah, we call it, and L is equal to 2, of course, in this case, yeah? And let's say these neurons take inputs like this, yeah? Each input gets sent to both neurons. Then the weights here will be W11 of 1, right? And then this one will be W12 of 1 by our convention. Yeah, just have to be, you have to use a bit of a care to do your record keeping of the indexes. Yeah, nothing really mysterious about these labels. Yeah, this is 2, 1 of 1, and then finally the weight. The last one is W22 of 1, right? Yeah? Yes? Mm-hmm. Oh, yeah. Well, this is 2, yeah. This is 2. This is all 2, yeah. L is equal to 2, so I should have just written 2 instead of L, yeah. Sorry about that. Thank you. So with this, then we can do, we can calculate the gradient using backpropagation. We start from the last layer, yeah, layer 2, right? And we says that, well, delta 1 of 2. That's what mainly we need to calculate. Yeah. Since this is the last layer, and last layer has one neuron, this is relatively easy. We just do partial E, partial x1 of 2, and then this partial x1 of 2, partial s1 of 2, right? Yeah. So this E, of course, it's we have I didn't write it yet. Yeah? E of omega, we define it as let's say the 2 norm. Yeah. So this 2 minus y squared, right? Yeah. Not 2. 2 norm. It's a square error. In that case, then this partial derivative is simple. It's simply 2 times x1 of 2 minus y, right? And then the next one, we already know this will be sigma theta prime of s1 of 2. Yeah, in fact, we've seen the example like this last time already, right? So once you calculate this delta, then we plug into our formula, the formula we derived already. It says that, well, then this partial derivative with respect to the weight, W11 of 2 is equal to, it's a matrix, but then, no, actually not this one, it's just simply x1 of 1, right? So I'm just going back to this formula here, right there, right here, yeah? But then since we only have a single neuron, so these vectors are just they're just scalars, x1 of 1, and then delta 1 of 2, right? Yeah. Just by the formula we derived. And then this, for the second weight, this would be 2, 1 of 2. Yeah. This will be, of course, x2 of 1 times delta 1 of 2. Right? Oh. Okay. And of course, we already have delta 1 of 2 above there, and substitute everything in. Then you find the derivatives at this layer. Yeah. Again, nothing new, right? So as I said, this part of the example is not that exciting, right? It's just repeating the formula. And then for the layer 1, we go back, and so we have to calculate this delta 1, yeah, delta 1, 1. And again, by our formula, the formula says what? Looks like this, right? The weights multiplying the previous delta, or the next layer's delta, and then you multiply by theta prime, yeah? Just going by this formula there for delta, then, since we don't have actually a single line, the weights, not a big matrix, simply this one item turns out in this simple example. And then delta 1 of 2, yeah, the next layer is delta. And then we multiply by theta prime as 1 of 1, just like that. Yeah? Then we're all set for this one. And then delta 2 of 1, similarly, here instead of W1, turns out that we get W2, 1, that's all. There's a certain pattern to it, yeah? And this one would be delta 1 of 2, and then theta prime as 2 of 1. Yeah. That's all. And then we substitute in that formula again to find the partial derivatives with respect to W. Yeah, for any I and j, yeah, and simply xi of 0 multiplying delta j of 1. Yeah. And this is for ij that are either 1 or 2. Yeah. So therefore, there are 4 different combinations here. That's all. Yeah, 4 different combinations of x's and deltas. So that's it, right? Well, altogether, we have, if you look at the figure, we have 4 different weights in this neural network. And now we have managed to find 6 different weights. Sorry, 6 different weights. Altogether, we have 6 different partial derivatives. Then we're all set, yeah? In terms of the backpropagation to find the gradient, yeah? We're all done. Okay? Now, so again, this part is just plugging in formula, yeah? Nothing to it. But let's take a look at 2 more things. First thing is that we can do more. Actually, we can further push back this idea of backpropagation to study not just the sensitivity to the S values. See, backpropagation use delta is the sensitivity to S values, right? We can push even back 1 more layer back to the original inputs to the neural network to study the sensitivity to the input of the neural network. Yeah? So, for example, we can say, well, what is partial E, partial x1 of 0? Okay, so x1 of 0, of course, is just the x1 in the original neural network, yeah, on top there. So you notice, how do we figure out this partial derivative? Again, the method that we have used before still applies. So we know that E of omega at the end depends on this whole thing, but how does it go through this whole thing and then depend on this x1? We want to find the relationship between the E of omega and x1, or more precisely, sensitivity of E of omega to x1, right? And then we'll say, well, this is going to be a composite function of many things in the middle, right? In particular, it is going to be a composite function of that involves S1 of 1 and S2 of 1. Yeah, because this x1 impacts E of omega through those 2 variables. Yeah? So there are 2 paths for the information contained in x1 to get to the end, get to E of omega. There are 2 paths that goes through S1 and S2. And we have seen this before, right? Something similar that we have done last time. And in that case, we'll just use the more complicated form of differentiation by using the chain rule. Yeah, the chain rule of differentiation. But it's a more complicated form, that's all. Yeah? So we have, because x1 goes through S1, 1, and S2 of 1 to go to E, so we know that to find the partial of E, then we can do partial of S1 of 1, and then partial S1 of 1, partial x1, plus partial S2, right? S2 of 1, and then partial S2 of 1, like that. Yeah? Okay. Just a fancier form of the chain rule of differentiation. Yes? Where? Okay. And of course, we already have the first partial because it's simply the delta 1 of 1. Yeah. The second one, well, because the S over there is just the just a weighted sum of the input x1, and the coefficient in front is simply W11. Yeah. And then the second one is delta 2 of 1, and then the coefficient in front is W21, 1, 2 of 1. Yeah. Then you're all set. And likewise, you can also find this partial derivative with respect to x2 at the input. Yeah, just and just by symmetry, you can see that this is equal to sigma 1 of 1, W12 of 1, plus delta 2 of 1, and then W22 of 1. Yeah. So again, yes. W. Which one? Oh yeah. Thank you. This is 2-1, of course. Yes, from the second input to the first neuron. Yeah. Good. Thank you. Very good. So these terms, this again is a sensitivity to the input of the neural network. Yeah, of the final result to input of neural network. Yeah. Now the question is, why do we want to know this? Why do we want to find a way to calculate the sensitivity of the error to the input? What is the benefit of knowing that? Or in other words, when we design a neural network, why might you want to know whether your neural network is sensitive to the input or not? Why? Yeah?
Because if you have outliers during evaluations,
That's right, yeah. If your neural network is very sensitive to any changes in the input, then for example, it might pick up the noise in the input very easily. Yeah, amplifies the noise. A little bit change, it reacts a lot. Yeah. A second thing is that even if your input is not noisy, you still might not want your neural network to be very sensitive to the small changes in input, because that means you might have a chaotic system. Yeah, that's the definition of a chaotic system. Yeah, very small input leads to a very large output. Yeah, so we just want to avoid that. Therefore, by checking this, you will see whether your neural network is designed is designed well. Yeah, a well-designed neural network should not be too sensitive to the input. So maybe let's say sensitivity. Let's say sensitive to noise. Yeah, then you have what we call overfitting. Right, we've seen that before. And if you are very sensitive just to changes in the actual input, even though it's not noise, then we risk getting a chaotic system. So that's the first thing. We can push our backpropagation idea further all the way to the front. The second thing is that so far, when we study backpropagation, there's an implicit assumption that I did not mention, but you might have picked it up, that we assume that these weights, they are all independent of each other. Right? The weights, they are individual items, so they don't have any relationship with each other. Okay? And this is the kind of the simple form of a neural network. But it turns out that we now know that in a neural network, you might want those weights to be dependent on each other. You might want to impose some constraints on them. For example, in a convolutional neural network, yeah, you might have heard of the term convolutional neural network. That is the current state of the art for image recognition. Yeah, why is it good? Well, convolution is simply the convolution that you have seen in your signal systems course. And there, with convolution, what can you do? You can do filtering, right? And for filtering, you can do high-pass filtering, low-pass filtering. High-pass filtering gives you the outline of an image, yeah, the edges, because it picks out the high-frequency part. Right? Low-pass filtering removes the noise, make the image look cleaner. Yeah? Both of them are helpful for you to process the image, at least in the earlier layers of the neural network. Then you send to the later layer to identify the image. Yeah? Clearly, right, getting an outline, say, of an animal or face helps the neural network to identify what the object is. Okay? So convolutional neural networks are very powerful in image recognition. But to build a convolutional filter, yeah, requires you to constrain those weights to have a certain form. Those weights have to be linearly related. Okay, for example, just simple example, W1 plus W2 has to be equal to W3, for example. Yeah, these kind of relationships. Okay, so far we don't assume that, right? We don't have that in our backpropagation formulation. Okay, but I just want to show you with a very simple example that it can work still, even with this kind of dependencies between the weights. So, for example, just to get a taste, yeah, simple example. What if we want to force the W12 of 1 is equal to W21 of 1, and then we just call it W like that, okay? So in that sense, in our figure above, then that means that we have x1 of 0, x2 of 0. Well, we send this in. These two neurons, right, like that. The first way there is 1, 1. W11 of 1 is unchanged, yeah. But W12, this we call it W now, is the same as the other one, W21. And then W22 remains unchanged, like that. Okay? Very often, in more powerful neural networks, we require something like this. Yeah. So, what do we do in this case? So again, this is useful for, let's say, for example, convolutional neural networks. Yeah? Okay. But we still need to find the partial derivative with respect to this W in order to carry out our gradient descent, right? Okay, so our previous method will not directly be applicable. Yeah. So first thing you notice that, well, if I want to find the this with respect to 1, 1, and 1, this is unchanged. Yeah. Right, and the other one as well. Is it 2, 2? Yeah, unchanged. Right. Because they don't have any dependency with W. But of course, now we have to worry about this guy, yeah? Delta, partial E and partial W. How should we find this partial derivative then? We already have enough knowledge to do this. Yeah, you have seen this enough. It's slightly tricky, yeah? So how do you do it? So let me write this, label this now, yeah, 1, S1, S2, just like that, yeah? And then it goes on. We use the same idea, right? To find this partial derivative, we want to know how does the information in W impact this E at the end, right? Yeah? How does any change in W impact the value of E? What pathway does it go through to get to at the end to E? Yeah? So what kind of composite function do we have over here? So this W now, if you change W, you will change both S11 and S21. Yeah? Previously, each one of them, each edge only changed one of the neurons. Yeah? Now this W, the same W, changes both neurons. But we have seen this before, we have done this before, right? That's all that we need. So because it changes these two things, we just use that more complicated form of chain rule of differentiation. That's all. So this is partial E, partial S1 of 1, again, partial S1 of 1, partial W, plus partial E, partial S2 of 1, partial S2 of 1, partial W. Yep. And of course, we know what this is. All right. So of course, this one is delta 1 of 1. And then this one still just x1, 1, x2. Oh, yeah, be careful, yeah. This, with respect to W for S1, actually the edges goes down, right? So it's like x2 over there for that one. So not x1 as one might expect. And then the second one is delta 2 of 1, and then x1 of 0. Yeah? Yeah. So therefore, the idea is that it can be done. Okay? And of course, when you go to more complicated networks, AlexNet or VGG and so on, those convolutional networks, the interdependency of the weights are much more complicated, but there is always a way, similarly, to find the gradient with respect to the weights. Okay. In fact, you can design any fancy neural network that can do very, very good job in terms of image recognition or whatever. Yeah. But people will use your neural network only if your neural network allows backpropagation for efficient computation of the gradient, right? Otherwise, nobody can train your neural network. Yeah. In any reasonable size neural network, the queue is too big. Yeah. If you don't have backpropagation. So all of the well-known and useful large-scale neural networks in the market or in the research literature right now, they all have to have some kind of a backpropagation to allow you to find the gradient in an efficient manner. But that is the kind of out of the scope of this course now. Yeah. For here, we'll just see that a taste of what can be done with backpropagation. Okay, any questions about backpropagation now before we move on to the implementational issues of neural networks? We're going to spend a bit more than an hour to talk about implementations. Turns out so far the techniques that we have discussed works very well if your neural network is reasonably sized and moderate size. But in this large-scale modern neural networks, there are some tricks that people have developed over the last 10, 15 years, numerical tricks that actually made them more efficient, and in some cases it made them work at all. Yeah? The large neural network, without this kind of tricks, the large neural networks actually don't work. So the first one is that when you design neural network, you have a choice of the activation function. Yeah? What kind of activation function are good in reality? So we already know if you, we already know a few already. Sigmoid is the one that we have seen. Something, it's a curvy shape going from 0 to 1. Yeah? And then we also say, well, if you want to have a negative values as well, which carries double the information, right? Then you might want to use a hyperbolic tangent. Yeah? ES minus ES minus ES like that, and then ES plus E minus S like this, right? And good thing about this hyperbolic tangent is that the derivative theta prime is easy to calculate, and you see in our backpropagation just now, right? We use the derivative of theta quite a lot, in fact, all the time. Yeah, so it's you certainly want to pick an activation function for which the derivative is easy to find. Yeah. But even this hyperbolic tangent form, people have discovered that when the neural network is large enough, that amount of calculation is still too much. Okay, and that hence the development, that something you have probably all heard of, the red rule activation function, yeah? The rectified linear unit. Rectifier, of course, rectifier as in EE, rectifier is a diode, yeah, that only goes one way. So, rectifier linear unit, short for red rule. Yeah. It does not allow any negative input to be passed on. Yeah, it's like a diode, no negative voltage allowed. Yeah, so if you draw this, of course, it looks when S is less than 0, it is simply output is 0, and then on the positive side, just output whatever input that comes in. Yeah, very simple. And I can see this is very easy to do any computation, right? In forward pass, you don't have to do any kind of e to the s or whatever calculation numerically. And also, in backward pass, if you look at the gradient, the gradient also very simple. Yeah, gradient s on this side is equal to 1 exactly, right? On the other side, the gradient is 0. Yeah, very simple. You just check whether the input is positive or negative. That's all. Yeah, no need for any extra calculation. So this, of course, is a default now in modern neural networks. Yeah, in modern network implementations, anyways. Yeah. So why is one reason is that this calculation is simple. There's a second, more subtle reason is that if you use a, say, hyperbolic tangent, hyperbolic tangent has this curve, right? So if you have a very large input coming in, it gets mapped to just 1, okay? So you lose the information. You cannot distinguish two very large numbers anymore, okay? So that's a trouble with some of these other curvy activation. So basically, this avoids some of the nonlinearity effects. For example, saturation of the hyperbolic tangent. Yeah, saturation means you just input too high, then the output just nearly 1, and it does not go any higher. But this one, it keeps going. Yeah? But of course, it cuts off the negative side. Clearly, we cannot simply use a linear line. Your activation function cannot be linear. What happens if your activation function is linear? Any thoughts? What if all of the activation functions are linear? Just a line. Why not do that, right? Why bother with cutting off something? Yeah? Yeah, not just approximate. They're exactly linear. All layers are linear. So overall, your neural network, entire neural network, is just a linear function. You cannot use it to represent any other kind of functions at all. Yeah? Again, if the activation functions are linear everywhere, then your entire neural network will be just linear combinations of the input, right? So you just, at the end, you just get a linear classifier or a linear regressor. Yeah, that's all that you can do, right? There's no point of using a neural network. Yeah? So in order for the neural network to be meaningful, the activation function has to be nonlinear. Yeah? Okay. Anyway, this is a default in the, anytime they say use PyTorch to grab a neural network from the library there, the default will be ReLU unless you specify otherwise, intentionally say I want to use something else. Yeah? So this is a very popular one. It has a lot of benefits, but then there's also some disadvantage that we have to watch out for. Yeah, which the main issue is that it leads to dead neurons. So if we say it's a neuron that comes in, yeah, and the xj of L, Sj of L. Yeah. So of course this comes in with from different weights. Yeah. Wi j of L. Yeah. So if at some point in time this input becomes negative, it can happen, right? Just some arbitrary combination of weights and input values. What happens then if it's a negative? It's red loop, right? So nothing passes out. So therefore xj, the output, becomes 0. Yeah? And at the same time, we know that the derivative, because it's negative side, is 0. Yeah? So all of your update, the backpropagation stops. Because remember, this thing gets multiplied to the backpropagation formula, right? So the backpropagation becomes 0. Yeah. This ij of L equals, remember, it's xi L minus 1 delta L, right? Again, you plug in the formula, you see that this theta prime shows up in the formula. Yeah? So this goes to 0 for all I. Yeah? So turns out that in this case, then the weights are no longer updated. Right? Because when the gradient is 0, you don't update it. You update nothing. You don't change your W anymore. Kind of get stuck there. Yeah? And eventually, it turns out that numerically, people have observed that it causes about 40% of the neurons in this state, which is dead. Yeah? They're dead neurons, they don't do anything anymore. Yeah? The output 0, right? Basically, then you can take away this neuron, it will not change anything. Yeah? They don't participate in learning anymore. Which is, of course, it's inefficient. Yeah? Yes. Oh, they're dead neurons in this case. When the output is 0. The output of the neurons, 40% of the neurons will just output 0. Yeah, in a large-scale neural network, roughly 40% would be like that. That's the no mathematical proof, right? It's just observational. Yeah, numerically, people see this, and it's just just a kind of wasteful resources, right? You spend a lot of time training these neurons, but at the end, you find out that 40% of them they are not doing anything at the end. Yeah, but that's what you have to pay. It turns out that you have to pay in order to gain the efficiency, in order to gain the advantage that you see up there. Yeah. Easy calculation and so on. So still, people find this trade-off to be acceptable, and that's why in modern neural networks, this is the default still. Just to know that every time you train a large neural network, just to expect that a lot of them will be dead, and that will impact a lot of things that we'll do a bit later. Okay, you'll see. So there are some proposals to address this issue. One is so-called leaky ReLU. So the idea is that on the left-hand side, you don't set it to 0. You set it to a linear line with a small slope, that's all. Yeah? So this one, you want it to be on the right-hand side when s is equal to greater than 0 is still the same. But the left-hand side, instead of setting to 0, you set it to a small number. So on this side, it's still the same, but at 0, you use a small slope like this. Still nonlinear, right? Yeah. But then you don't kill the neuron basically when the input is negative. A common example would be alpha is equal to 0.1. Yeah. But this is not very popular because again, it requires more calculation and so on. And the ReLU, people think it's still worth it. But you can choose this as an option, I think, in most of the libraries. There's another one. You say, well, how do I know how to choose this alpha value? Yeah. A recent paper developed a new method called parametric red rule, where you learn the appropriate alpha value from your data. Yeah. This is 2015. Some of these more recent papers says that basically alpha is selected during training. Okay. But these are the more kind of advanced methods that is outside of the scope of our study here. But this one I don't know whether most libraries will have, but Leaky certainly I've seen. So that's the activation function. The second issue in implementation is input preprocessing. We usually do not want to just take whatever input we're given and then just dump it into a neural network. That turns out to be highly inefficient. We want to process our input a little bit first. So input preprocessing. Okay. So there are two things that we want to discuss. First one is normalization. Basically, you want to normalize your input to have a zero mean and univariance. Okay. So let's say the data points looks like this: a set of x1, y1, to say n points. Yeah? You have these data points, and why do we want to normalize them? One example is that our x, let's say it is a data set with a bank. The credit card credit scores, yeah, and in that case, then the x will be the person's attributes, right? Let's say for credit scores, the salary will be an important thing, of course, right? Another important element might be the number of children that you have to support at home, yeah, how much you have to pay every day to raise your children. So number of children usually is an important element in that vector of attributes for a person's credit score. Do you see a problem now with these two? Say, why do you want to normalize? Yeah?
Like salary can be very large.
Yes?
Like number of
Yeah. For you guys with say machine learning background, you go out there, you get $100,000 salary, 100,000 number, right? And then number of children, well, maybe 2, you know? So huge difference, right? If you just send this thing into the neural network, what happens? The salary dominates the whole neural network, which is so much bigger than the other value, right? This becomes negligible. But you don't want that, right? You want this one also as you want also consider this, the impact of number of children as well, yeah? So therefore, we want to normalize them so that they are all on the same scale before you pass your input data into the neural network. That makes sense, right? Yeah? So the question is, how do you normalize? And it turns out that we have done this a lot of times in your maybe probabilities course. Yeah? How do you normalize a random variable to a zero mean univariate random variable? Yeah? Shift the mean divided by the standard deviation, right? That's all that you need to do. Yeah? So let's say we calculate the sample mean. We don't have the true mean, of course. We won't have the data. Yeah? So we have to calculate sample mean. And we have n samples. Therefore, the sample mean, if you look at this vector of mean values, is 1 over n. And then you sum up xn, right? This is the sample mean. You use this to approximate the true mean value of your random variable, right? And then we want to know this standard deviation as well so that we can normalize. And therefore, we need to calculate sample standard deviation. And we call it sigma bar. And if you learn your statistics as well, then you know that take the sample standard deviation, you have to use 1 over n minus 1 to get an unbiased estimation. But this one is not very important when n is very large. Yeah. So this, for all of the samples you have, you just take a mean shifted version. Take the square, you get the sample variance, right? And then you take the square root, the big square root, you get the sample standard deviation. Yeah. Again, I just want to emphasize this is when you have big data, whether you use 1 over n or 1 over n minus 1 is not that important. Yeah. So, but strictly speaking, you should use 1 over n minus 1. That's the more appropriate form. And then once you have that, you then just normalize. Yeah, so you're going to normalize each element of x, xn, in fact. For every sample, you do this for every element of that input to have 0 mean and univariance. Yeah, so to do this again, you just shift by the mean value and then divide by sigma. Now these are vectors, so we have to specify that these are pointwise divisions. Yeah. For every element, you do the same thing. For every element, you shift by the mean, divide by the standard deviation of the element. Okay. So that's it. Simple as that, right? Nothing really new here if you already know this from your probabilities course. Yeah. Okay, we'll stop here, take a break, and we'll come back at 1:10. Yeah. By the way, I cannot find a room for Thursday's midterm. So I'm thinking maybe we'll have to make the midterm on Wednesday and then make Thursday the alternative date. Okay. I know that on Wednesday there are more conflicts, so I have to resolve this issue. So wait for my announcement. Okay. Let's restart. All right, let's start again. So the second thing about input preprocessing that we just briefly mentioned is data augmentation. Not only we want to just simply normalize them, normalize your data points, you also want to maybe select the most important parts, or sometimes even rotate them so that they align in a certain dimension better. Yeah. So in general, this would be you have x and y. Each data point, you first run some kind of a transform. Yeah. In order, we have seen one of this before, right? We see, well, if originally you have in a non-linear domain, you transform it. Hopefully, in the new domain is linear. Yeah. But this is more general. Yeah. This is more general in the sense that you can maybe even rotate your data points in hyperspace. You can flip it. You can take a subset, subspace, and so on. Yeah, can be rotation, yeah. Can be flipping, could be cropped, yeah. Scaling, all of that. Okay. Just so that you want to make your data into a form that is easier for the neural network to process. Okay, for whatever reason. Yeah, one of the big reasons would be a lower dimensional data. Yeah, if you have your original dimension has thousands and thousands or millions of dimensions, you might want to compress it a bit into a form that's easier to digest by the neural network. And one common method of this is the PCA, the principal component analysis. From the name, you just see that you want to the different components of the your input. You want to find the most important ones, the principal ones. Okay, so and then you just send those important ones into the neural network. Yeah, that, in some sense. Yeah, but not only can you choose dimensions, you can also rotate them first, so that those dimensions you pick has the highest concentration of useful information. Now, exactly what that means is too deep for us to discuss, but it has to do with eigenvalue decomposition and singular value decomposition, those nice things about linear algebra that you might have learned before. Okay, so we wouldn't have time, turns out, to cover this topic. So I just mentioned that there is such a thing that people usually want to do, especially when you go to large big data and big neural networks. So that's that for input data processing. The third common thing that we do that have to worry about is a weight initialization. Yeah. When we train a neural network, we start from an initial weight, right? A set of initial weights, and then we do backpropagation and update those weights. Where do we initialize it to? Yeah. If you say initialize them all to 0, will it work? Will not, right? With all 0, then forward propagation give you all 0. You get nothing, yeah, in the backpropagation. So it will not work. You have to initialize something. But what are the concerns when you initialize your neural network? If the weights are too large, yeah. If they are initializing all to 0, what happens? In your backpropagation, you do, yeah, you do forward step first, right? They're all 0, and come back, they're all 0 again. There's nothing changed, nothing. Yeah. So it has to be some non-zero value, but what if it's too large? You have to worry about that, right? In large-scale deep learning, you have many, many layers, okay? So if the weights are large, what happens when you have many, many layers? remember this layer's values multiply the weights sent to the next layer, right? If the weights are big, that means every layer you amplify the signal by a lot, yeah? Every single layer you amplify the signal by a lot. Until, if you have many layers, those numbers get huge, yeah? What happens when you have big numbers in numerical computation? You get numerical errors, right? And sometimes your registers might overflow. Yeah, you cannot hold such a big number anymore. Again, you multiply the same thing many, many times, right? Yeah, then you get a huge number, exponentially fast. Yeah, so even when your registers don't overflow, if your activation function is of a form that clips the values, then if your values are large, then they'll all be clipped, yeah, like the hyperbolic tangent. Yeah, they all get mapped to 1. Yeah, you lose all of the information. So we don't want the weights to be too large, right? So large weights. What are the problems? Signal grows. Over layers. Does it become too massive? To be useful. Okay. And what the opposite? Then I'll keep my weights small, right? What's the problem then? Yeah. What happens when you have small weights? Could be, yeah. That's. But there's a more precise way to put the same idea, I think. Yeah, they just disappear because, again, layer by layer, you multiply by these small weights. They get smaller and smaller. Yeah, so if half, right? First layer you get half, next layer is 1/4, and then 1/8. Very quickly it goes down to 0, right? Close to 0, and then your number is so small that it's very hard to handle anymore. And you also again get numerical errors. So let's say vanishing gradients, yeah, or vanishing information. Especially in deep neural networks. Deep neural networks means that you have many, many layers. The weights are too small to transfer any information between layers. Yeah. So therefore, you have to have a good way to do initialization. You have to pick the right size. But what is the rule of thumb then, right? You don't, remember these two problems, right? You don't want the signals to become bigger and bigger. You also don't want the signals to become smaller and smaller over the layers. Ideally, what you want, the signals about the same size between layers. Yeah? So therefore, you might want the weights to have a magnitude of, say, 1, right? Roughly. For each layer at the end, after you multiply the weights, you get roughly, say, same amplitude 1. Because remember, we already normalized the input to have amplitude of 1, right? Yeah? So now if you maintain each layer's input to be 1 as well, then we're all set. Yeah? And roughly, there's no explosion of signal, also no vanishing of signal. So based on this idea, this person, a student called Javier Glorot, maybe French name, maybe, who's in Yashua Bengio's group, Yashua Bengio in Montreal, who is also a former, I think, a postdoc, a student of Jeff Hinton at U of T. So there's basically the third generation, right, from Hinton's group, proposed this method, so called Javier initialization. That was 2010. So this is a popular one that again is in the library that you can find. First of all, the bias weights, right? Starting from 0, they are bias weights. Yeah. So you set them to be very small, or just 0. That's fine. And then for the other weights, when you initialize them, you set them to a Gaussian random variable with 0 mean, and then 1/n variance, where n is, for that particular layer, equal to the number of neurons in the layer. So dl minus 1. Okay? Basically, the left-hand side neurons of this edge. Yeah? So again, this is a Gaussian, right, with 0 mean and variance 1/n. I think you're all familiar with this notation, right? I don't have to write it down. No? Okay, write it down. Okay. Gaussian with mean equal to 0, and then the variance equal to 1/n. Not the standard deviation, okay, mind you, it's the variance, 1/n. Okay? The m, the scripted m there stands for normal. We have the normal distribution, which is also Gaussian distribution. Okay. So why does this work? Yeah? Why does this initialization work? Okay. The explanation is following. We recall the formula. As I said, you want to maintain the layer by layer, the input to the different layers to have one variance, yeah, about the same size. Right? So you look at Sj, this is the input to the layer L, right? So this is I equals to 1 to d L minus 1. Yeah? Just summing up the weighted sum of the outputs from the previous layer. Yeah? Right? That's what we have before. Just describing the neural network. What is the variance of this one? Yeah? Can we see that it's roughly is 1? Yeah? That's what we want, right? So what is the variance of this guy? Now you have to go back to your probability course, right? This is a sum of random variables. We already know that this one we have tried to normalize to 1, right? Yeah? We at least the first layer, we normalize to 1. So how about the second layer? And then we have this S now. So if this has variance 1 already, then what is this thing altogether? So assume that all of these random variables are independent. Okay? In reality, they are not. Okay? But roughly, if they're independent, then the sum of random variables, the variance of the sum equals to, if you have independent random variables, the variance of their sum equals to the sum of the variances. Very good. Yeah? Variance of the sum equals to the sum of variances. In that case, then therefore this is roughly equal to the variance of W is 1/n already, right? So 1/n times this I equals to d of L minus 1, and then the xi minus 1. This one square, right? I'm sorry. Yeah, square. Yeah. But that one roughly has a variance of 1 on average. Yeah? On average, it's 1. So this is approximately normalized. So therefore, this whole thing is roughly equal to 1. Okay? We can say that this is approximately normalized in each layer because we have been trying this, right? We set the weight to be of this form. So, and then the first layer is x is normalized, and then the whole is that layer by layer, roughly they are normalized to 1. Yeah, there's a balance of power in every layer, roughly. Yeah, and just by induction, you go down the layers, you always get 1, 1, 1, 1 for the variance. Okay, somewhat hand-waving argument again, yeah, because they are not independent random variables. Okay, but roughly speaking, that's the motivation, anyways, for this initialization. Yes. Because this is only works if those are independent random variables. In general, they are not. During training, they are they're complicated dependencies among these variables. If you have independent random variables, then the variance of their sum equals the sum of their variances. Yeah. But only works if they're independent. So again, so this is a very popular method and proposed a while ago. But there are also other choices because this one, as I said, this is only approximate, right? So people have proposed other variants. In fact, the first variance is actually still from the same guys, from Harvey, same paper, in fact. So over here, this n is the number of incoming neurons to this edge. Okay. What about the outgoing neurons? Yeah, the outgoing edges. So you can do that too. So we can account for that as well. Your question.
For the approximately normalized, isn't that only true if it's the applied Batch normalization?
Explain more, what do you mean by Batch normalization?
Oh wait, we talked about normalization.
It's only input normalization. Now we just talk about the input values normalization. We're not talking about batch.
Okay.
Yeah.
Yeah, but I
Yeah.
meant only if it's normalized, right?
Yeah, oh yeah. You assume at the beginning you normalize them to have variance 1, right? That's why these guys, we assume that these guys have about roughly 1.
I'm confused. Do we always normalize? I thought batch normalization was an option. So doesn't this no longer work if you don't do that?
Yeah. So all of this have to, again, hand waving the weave together. Yeah, and you have to do experimental things and you have to tune all these hyperparameters. How do you normalize and so on? They are all part of the tuning, really. Yeah. But for now, all of this is based on the assumption that at the beginning you normalize the input to have variance 1, and then you do this weight. And even then, there's no guarantee that they don't do anything funny, right? We just say roughly, yeah, probably this will work. Okay. Most of this that's why these are implementational issues. Yeah, there's no theoretical proof on any of this stuff. So another choice is to say, well, let's take the average between the incoming nodes and the number of outgoing nodes in the next layer. So we have number of units in plus the number of units out, instead of just accounting for the number of units out, number of units in. Yeah. So you just take the average of those two to set the variance. That might work better because you go back and forth. Who knows? But it turns out, yeah. In some cases, this one works better than the other, but sometimes not quite. So, but it is a choice. Another choice is not use Gaussian, but rather use a normal distribution. But you still want to keep the variance to be 1 over n. That's something that people have used, and it seems to be reasonable as well. A uniform random variable between minus square root of 6 and square root of 6 like this will give you the unit variance, turns out. Okay. And there are other choices as well, but none of them is really theoretical, but numerically they seem to work well. I think one thing to know here is that the bias weights, usually we initialize them to be small, and that's okay. In fact, most of the time you simply set it to 0, and there's no problem, I think, for most of the architectures. Now, if you use ReLU, though, as activation, what happens then? What do we need to do? Remember ReLU, what is the big property of ReLU? About half of the neurons will die. Yeah? So now if you still set the weight to have the same weight, then from one layer to the next layer, you actually, the amount of signal drops by half. You actually get the exponential decrease in terms of signal strength, right? So if you use red rule, you don't take care of the weights, you actually would not work over a deep neural network. Yeah. So what is the simple way to counter the impact of red rule? Well, just boost the weights, double the weights, right? Double the size of the weights, the variance, anyways. Yeah, the power. Yeah. So variance of this. You want to set it to be maybe 2 divided by n instead of 1 over n. Yeah. And these things are so hand waving, right? I'm not even saying 1 over 0.4. We know that about 40% of them die, right? If you want to be exact, should have been 1 over 0.4, yeah, which is that 5 over 2. Yeah. But all these things are so wishy-washy that normally just say, well, 2 is good enough. It's approximately equal to 1 over 0.4. Doesn't matter, yeah? Okay. Because we know that roughly half of the neurons would die. Yeah. Become inactive. Yeah, just consider this a rule of thumb type of implementational issues. The next one, yes? Oh, just because for uniform random variable, if you want to keep the variance to be 1, then you need the boundary to be minus square root of 6 to square root of 6, that's all. The next topic is called dropout. If you have implemented your neural networks on PyTorch or TensorFlow, you have seen this option already. Yeah, but what is it? What is dropout? Yes.
Okay, so random just picks like numbers higher than 0. So why don't we just set the weights to be above 0 initially? That way, like the outputs.
No. The output x could be negative, right? The weights being positive is not enough.
Okay.
Yeah. So the idea of dropout is very simple. They said during the training, in every iteration, you randomly throw away some neurons, or you inactivate some neurons. Train for this step, but then in the next iteration, you bring them back, but then you kill another set of neurons. Okay, that's what dropout is. So during training, in each of the SGD step, update, and then for each neuron, including the input nodes as well. So let's say for each node, with probability, say rho, set its output to 0. So basically, you make it inactive, right? You just don't let it participate. Force it to be quiet in the forward pass. Okay. Again, notice that in the next iteration, you bring them back, but then you inactivate a different set. Yeah. So all picked by random. Yeah, with probability rho. Yeah. How does this help anything? Yeah. But first of all, there's no strict, rigorous mathematical reasoning behind this. But at least we can see a little bit when we look at our formula for the gradient. For this partial derivative, it's equal to xj l minus 1 delta j of l. Right here, you can see that if you set the output to be 0, then the gradient becomes 0. Right? Yeah. The gradient of the some edges. In fact, if you look at all of this math carefully, you see that both the incoming edges and the outgoing edges of this neuron that you set to be inactive, their gradient becomes 0. Okay? So during the backpropagation, for these neurons that are inactivated, their edges basically frozen. They are not changed. Yeah? the weight of inactivated or inactive, let me say just inactive nodes are not updated. Okay. And also because the output is 0, that neuron does not participate, right? So suppose originally you have a 3-layer neural network that looks like this, slightly more complicated than what we have seen so far. Maybe fully connected like this. Yeah, maybe. Like this, yeah? And you decide to, well, in this particular pass of the SGD, I'm going to inactivate these two, yeah, get rid of them, okay? So because they output 0, right? So as if those two neurons do not exist anymore, and their weights are frozen. So the new neural network looks like this. Yeah, right? Those two just disappear. You have a simpler neural network like that. Okay. So why does this work? And numerically have been shown to work very well. In fact, without dropout, some of those large neural networks are very, very hard to train. Yeah. Dropout makes it much easier to train for some reason. And there's some hand-waving argument for this. First of all, by randomly dropping some neurons over time and then bring them back and so on, no single neuron can dominate the network. Yeah. Right? That's obvious. And even if you have a neuron that is not particularly well trained, maybe behaving a bit strange, it cannot dominate. Yeah. The second, a more interesting argument is that to find a good solution to a problem, we might want to try many different versions of a neural network. Okay? And this is called ensemble learning. Okay? For example, I can train 10 different neural networks and then observe their performance using my validation data and pick the best one. Okay? That's called ensemble learning. But that is, you pay a price for that, right? You have to do this 10 times. You know, neural network training can take a lot of time, a lot of energy. Yeah? Okay? So you don't want to do it 10 times necessarily all the time. So by doing this, what happened here is that over time, because you inactivate different neural networks, and then every time you inactivate a subset, you get a new look, and get a new architecture for the neural network. Okay? So in some way, you're trying different architectures. You're trying different neural networks over time. Yeah? And eventually, it converges to the best one. That's the argument anyways. Yeah? It's not mathematically rigorous at all, no proof. In fact, nobody really knows why it works. I don't know if you ask Professor Hinton. By the way, this developed by Hinton's group again in 2014. You ask, I don't know what he would say, yeah? But from as far as I can read in papers and books, nobody really knows why it works. Yeah? There's only hand-waving arguments. So this is one of them. So basically, we are trying multiple neural networks at the same time. Okay, so a kind of efficient way to do ensemble learning. Yeah, you don't have to separately train many neural networks because this randomness, you're trying many different neural networks at the same time, right? Yeah, many of them. One thing to know is that if you do use dropout option, then at the end, after you finish training, you use the entire network. Yeah, all of the neurons will be there, right? Because they're only temporarily deactivated or inactive. Okay. But since now you bring back some new neurons, you have to adjust your weights, yeah, so that you correctly account for the fact that now you bring back these neurons that were not there in training. So suppose initially you drop out, say, 20% of your neurons, right? All the time. You only have 80% of your neurons. And now suddenly in the testing, you put them 100% back. Yeah? The signal strengths will be very different from during training, right? To account for that, you have to adjust your weight values. Yeah? So you have to scale down the weight values because now you have more neurons to participate in testing. Okay? Right? So we have to scale back, scale the weights by a factor of course, 1 minus rho, yeah, because that's just that's the right proportion, yeah, the remaining ones. Yeah, okay. So rho is between 0 and 1, right? It's a probability. So you are decreasing the weights, right? By doing this, you decrease your weights because now you have more neurons, which makes sense. Yeah. Again, makes sense in the hand-waving fashion. Yeah? None of this is exact. That's something that really bothers the community. Yeah? When we work with neural networks, just a lot of this is hand-waving. All right. Another topic for implementation is the SGD itself. Okay. Turns out that the current SGD that we have, even the one with momentum, is not enough when you have to train large-scale neural networks, because neural networks are highly non-convex. You know, if you look at the surface of a neural network, it looks very, very strange. Yeah, imagine the moon, the surface of the moon. You know, you see potholes everywhere and so on. Now on that surface, you want to find the lowest point. Imagine how difficult it is. And the moon is only two-dimensional surface, right? Imagine this is a ultra high dimensional surface in hypersphere, yeah, that you have to find the lowest point. So we really have to get better methods. So variation of SGD. Yeah. And this is because neural networks are highly non-convex. In some strange shapes. So as a reminder, we have the basic SGD, of course. That says, well, you update the weights of the neural network, simply a learning rate multiplying the gradient, right? The negative the gradient to be more precise. And gradient of this f depending on whether you do full batch or single point or mini batch, yeah, mini batch. Whatever f is, yeah, doesn't matter. It's the same method, right? And we discussed before that if you add momentum to it, you can get over some of the valleys, shallow valleys, right? Or the those points there, saddle points, yeah. And also even for convex functions, you can speed up convergence by using momentum. Yeah, and the form looks like this. Your Vt, which is the momentum, it is basically accumulation of the past velocity, and then you add this new component of the velocity, right, just the gradient. So now you update the w, t plus 1. You can view the w as kind of like the location of a ball, right? V will be the velocity of the ball, yeah? So updating the location, you just add the velocity. And update the velocity, you just add the acceleration, right? the gradient serves as the acceleration for your velocity. But then you also remember some of the past velocity as well, like that. But yeah, again, this one is fine, but there's one big problem with this, is that you see the learning rate, the step size for update is the same for all dimensions of the gradient or the velocity, yeah, or the weights for all dimensions. But neural network, we have usually a high dimensional function, right? This W is very long, millions, billions, or trillions of elements, right? This is the W that we have, right? Our number of parameters, right? Millions, billions to trillions. Many, many of these, they cannot all use the same rate, right? The same learning rate cannot be appropriate for all of them, really, right? In some dimensions, there's so many dimensions. Some dimensions, the curve must be steeper. In some other dimensions, the curve must be shallower, right? So we know that for the steeper gradient, we should use a smaller step size because we want to be more cautious. Because every step you change a lot, right? In shallower parts, shallow directions, we might want to we can use a larger step size, right? So that's the idea. We want to use different step sizes or different learning rates for different directions, okay? And this is the idea of the ADA-GRAD, adaptive gradient. ADA-GRAD method, 2011. So idea, we want to vary the learning rate across different dimensions. Yeah. So how do you do that? Well, you want to remember the gradient in the past, and then use that to adjust your step size. Yeah. So how do I remember the gradient in the past? Well, just take the square of this. So I do a pointwise multiplication of this gradient. So I get the square of the gradient value in each direction, right? So this is again pointwise multiplication, right? And then I use this square. So by the way, this is again basically accumulation of all history of the square gradient, right? Yeah. So you remember, okay, if in the past has been steep, then maybe now I want to be more cautious. I don't want to use a very large step size. Yes. Oh, yeah, there's a T. Yeah, thank you. Of course, thank you. And then now, when I update, I just use a constant epsilon like this, multiplying the gradient. But then now this is multiplying a inverse of this past gradient size, right? If I just keep CT, that will already make sense, right? If in the past I have very steep gradient, very large CT, then I tend to use smaller step size now, yeah? Okay, this epsilon naught is just to control that general size that we have for everyone, but this one CT is more specific to the particular direction, right? But usually we also add this, a small number for numerical stability, but just in case that some of them CT is nearly zero, yeah, especially when you get close to the optimal point, right? Yeah, so you add this small number for numerical stability. Okay. And this division here, because we're dividing a vector, right? This certainly would not work in general. So this one has to be pointwise division. Yeah. Okay. So by doing this, then you're giving a dimension-dependent factor to the learning rate. Yeah, so it makes sense. ADA-GRAD is a popular one for a long time. Of course, the advantage, again, as I said, smaller step size. along steeper directions, which seems to make sense as a good practice. Yeah. But turns out that there's a problem here with this method, that it accumulates all history. Can anyone tell me what might be a problem here? Well, turns out that in neural network optimization, usually it takes a long time. Okay, it's not like logistic regression. You just keep going down, and then you get to the bottom very nicely. Yeah, neural network, the surface is so complicated, you kind of struggle along quite a bit. Yeah, for a long time, and then suddenly you go to a cliff, you're lucky, you go to a cliff, and then you go down, okay? But while you're struggling along, you keep accumulating these values. This CT gets bigger and bigger and bigger and bigger, okay? So now your step size becomes very small, too small, in fact, okay? So that's a problem. So, pictorially, in neural network training, very often we just keep struggling around, and then suddenly it goes down like that. Okay, for neural network. So the problem is that in that case, the learning rate can decrease too fast, can vanish. Yeah. So basically, you get stuck over here, maybe. Yeah, just before you can. Before you get the chance to go to a much better point, the learning rate becomes too small. Yeah, because it's been a long time there. Yeah, these CTs just keep remembering the historical information, right? So how do we solve this problem? There's an easy way to solve this problem. Here we're saying that, well, this is a problem that you are accumulating too much of the gradient, right? Even though the gradient itself is not that deep. Gradient could be small, but then you accumulate for a long time. During the training, you already waited for a long time. So you accumulate a lot. So we don't want that. How do we avoid this? How do we avoiding too much of the historical information? How do you do it? How do you forget some of the history? Okay, that's a very strict cutoff, right? But there's a better way to do it, discounting the history, right? Discounting the past by using an alpha factor. Yeah, we have seen this before, right? So we can use a discounting factor. And that's the RMS prop idea, again from Hinton's group in 2012. Small improvement over undergrad. In fact, undergrad these days it's almost always run in this discounted fashion. Yeah. Where of course alpha is between 0 and 1. Yeah. So we'll that is gradually forget distant history. That works very well. But there's a small problem that now you have this additional parameter alpha to decide. Yeah, what should be the right alpha to use? This is another hyperparameter that you have to tune, right? One more hyper. Decide. Yeah? And hyperparameter tuning is time-consuming and very annoying as well. Yeah, very often you tune the hyperparameter for one application, it does not work for another one. Yeah, for one neural network, it does not work for another neural network. So very messy stuff. Yeah, so but you have to pay if you want to, forget the history. Yeah. Now, so far, this undergrad and RMS prop, they don't use momentum. Right? And of course, naturally, we can say, well, what if we combine them together? And people have tried this, and they work very well. At least in some applications. And how does this work? Well, very similar to what we've seen before. You have the CT also, alpha CT minus 1, and then plus 1 minus alpha of the FWT. Same thing as before. The CT updating does not change. Yeah, you just add this new VT quantity, right? Now we have to use beta times VT minus 1, and then minus this guy, the gradient, with a RMS prop way of adjusting the learning rate. Yeah, like that. And then you say, well, WT plus 1 is equal to WT plus VT. Yeah. So this is how you include momentum into anything, pretty much, right? Yeah. If you compare the basic SGD and SGD with momentum, it has the exact same form of adding the momentum. So nothing really new here. Yeah. But that leads to the final one that we have, the kind of the current state of the art, called ADAM. And this was published in 2015, and one of the authors is Jimmy Barr. Jimmy Barr, again, is one of the guys at U of T before. The ADAM is the current default for neural network training. If you grab, say, PyTorch library, ADAM would be the one to use. Yeah. Although you can also always choose simple SGD or even RMS prop. But ADAM usually is highly recommended. ADAM is nothing really special. It is a bit more complicated to explain here. But all that we need to know is that it is essentially RMS prop plus momentum with some adjustment. It's a rather tedious adjustment. Yeah. So that's why it's good to have those libraries. You just call the function and that's it. You don't think about what it does inside. Yeah? There's some rather messy correction factors that they put in. Yeah. Okay. These are the correction factors, a new part. Again, for the purpose of this course, you don't need to know what's inside. Just know that this is the current state of the art. The name of ADAM stands for Adaptive Momentum Estimate. Just it compares to ADAM. Yeah. It's successful, yeah, so everybody's using ADAM these days. So this is the current state of the art for implementation that we need to care about, and for your program assignment, the third one, yeah, you need to use some of these techniques because otherwise, to train a big network, it will not work. Yeah. So that's all for now, and then also this will be the coverage for the midterm, okay, until today. Next week, reading week, of course. Then we come back for another 1 week of lectures. Then we have the exam the week after. And in that week, we won't have one lecture because we're going to, I still try to find a room for Wednesday exam, yeah. We won't have lectures on Wednesday or Thursday in that week anyways, yeah. I'll make an announcement about the exact detail of the schedule and everything pretty soon, okay? Okay, enjoy your reading week. I'll see you when we come back.